It's Kusekwa boy, so I hope you are doing well, my guys. And so today we are just going for inorganic chemistry. Previously we started about the two subjectives, and so today we are just going for the extraction in organic chemistry. So we did the first, which was the inorganic chemistry, organic chemistry. So we did the first thing we discussed about the compounds of metals, metals, and we did about the carbonates. We did about the sulfates. We did about the chlorides. We did about the nitrates, and all the 6 compounds of metal that has been selected by the ministry. So today I'm just going to discuss with you about the extraction of metals, metals. This is only for Form 6 here, so it's not for Form 3s. So if you are in the room, make sure you leave out the room for your guys. So I'm just going to discuss with you about the metals, about 2 things. The first thing, I'm just going to discuss with you about the introductory concepts. And the second thing that we're just going to discuss, about the selected compounds of metals. So selected compounds of metals. Here we're just going to discuss about the 3 metals: tin, aluminium, and the copper. So for Form 6, we are just going to discuss about the only 3 selected metals depending on the reactivity. It's not like you are doing in a level. So let's start with the extraction. What's extraction does it mean? What does extraction mean after? Talk about the extraction of metals. This means we take out the metals from their metallic ores. Always metals, for you to understand about the extraction, you need to know actually about the natural occurrences of metals. Metals tends to occur depending on the reactivity position, the reactivity series. The most reactive metals tends to occur in combined form, in compounds or combined forms. These are what we speak about the reactive metals: reactive and moderate, most reactive and moderate reactive metals. This tends to occur in combined form, but for those which is less reactive metals, tends to occur just at the free elements. Less reactive. So the most reactive, like sodium, potassium, those metals tends to occur as combined form, like sodium chloride, potassium chloride. But talking about the moderate reactive, like we can say about the aluminium, tends to occur as oxides, like aluminium. The chief ore is about the bauxite, which is now aluminium 3 with 2 water of crystallization. So we speak about the natural currents. So metals always tend to occur depending on their position in the reactivity series. So for the less reactive, for example, the less reactive metals that we have, it's like mercury. You also we have gold. So those are less reactive metals found in the below the reactivity series. That's what we speak about the natural currents. So to understand about the extraction of metals, actually you need to understand about the natural currents, because the extraction methods, how we obtain the metals from their metallic ore, depends exactly on the nature of the impurities and the nature of the metal. Talking about the nature of metal is the position within the reactivity series, as I've spoken about. So let's speak about the extraction now. Simply, I just make it easy for you to understand about the extraction. We have the steps that you need to know exactly about the extraction of metal, and these steps are glycocarep. If you understand all about this, you have just covered all about the extraction of metal. So speaking about the extraction of metal, we have the 5 stages that you exactly need to understand them before doing any any procedure within the extraction of metal. So speaking about these stages, there are 5 stages for the extraction. So speaking about exactly about the extraction of metal, extraction of metals. What is it? Is the obtaining is the process of obtaining pure metals from their metallic ores. What are the metallic ores specifically? Metallic ores, speaking about the metallic ores, speaking about the metallic ores, we are speaking about the solid crystal by which the metal tends to occur naturally. It's about the solid crystals. In which a metal exists naturally. So a metal naturally exists in that form is what we speak the metallic ores. For example, you don't find aluminium just in the naturally. You just find it as aluminium oxide. We call it the bauxite. Bauxite for aluminium, castellite, we call it the stannic oxide, those are ores, for tin, but we can have what we speak, for example, copper, we can have the copper pyrites, which is copper, iron has the sulfur, so those are just examples of the metallic ores. So you need to know the objectives now. We have the 2 objectives here to understand the extraction of metals. The first thing that we need to understand, this subtopic number 1 in this extraction, you need to know about the steps for extraction. And second thing, you need to know about the selected compounds of selected metals, which I've just told you they are 3 actually. So speaking about this, let's speak about the steps used to extract metals from their metallic ores. Let's speak about the processes, the steps used in extraction of metals. Okay, so speaking about the steps taken, steps taken for extraction. Steps taken for the extraction. The first thing, we're just going to discuss about the grinding. So you just frame them by saying rep. So speaking about this is just the concentration. Number 3 is talking about the calcination. Number 4 is about the reduction process. Every metal follows these steps or more than these steps in order to be extracted. So the first step is turning. You need to know the first step. You take just the metallic ore and grind it. You crush it and then grind it into fine powders. That's the first step, just to make it fine, so as the chemical reactions can take easily through it, because the reaction takes place when there is a small surface area actually. But talking about the concentration, speaking about the concentration is now the physical removal of the impurities from the metallic ore. But speaking about the calcination, you burn in the presence of oxygen or in the small amount of oxygen. Here, if it's an oxide, you just calcinate it. You heat it in the absence of oxygen or in the limited amount of oxygen is what we speak about the calcination. But speaking about the roasting is now the burning in the present oxygen, so as to convert this concentrated metallic ore to be an oxide. So the fourth step will just be the reduction process. Reduction process. So speaking about the reduction now, that oxide which has been formed in calcination and roasting is being reduced into a metal which is actually not pure, which is an impure metal. For example, in copper we call it the blister copper. It's not pure actually. So speaking about the number 5 is purification. So you need to purify what you've got here. Purification. Hey, to make it easy for you, you make sure you understand in each step what is done and what is the product for that step. So let's start to speak about the grinding step. Grinding step of the metallic ore. Grinding step of the metallic ore. So speaking about the grinding, you can grind something without crushing it first. So you take the metallic ore as the solid, the metallic ore, and we say the crushing. In your book, Thai, they have just said crushing and pulverization. Crushing and the pulverization. Pulverization. Speaking about the crushing and pulverization, you start first by taking a metallic ore, metallic ore, then you crush it. Crushers, using the crushers, so to obtain the small particles. So what is being obtained here is about the small particles. These small particles are then being classified, ground, let's say grounding. What's the product here? The product should be the fine particles now. Fine particles. So actually, in the first step, which is crushing and pulverization, or we call the grinding, what is done is the metallic ore being crushed by using the crushers into the small particles. Then those small particles are ground into the fine particles. Now what is needed here in the grinding stage is about the fine particles, but there are a lot of steps here. You start first by crushing to form the particles and then grinding into the fine powder. Hey, and if the particles through the crushers passes which has the larger size than the required one, they are screened back. So they are passed through the screeners, and the screeners also can be either a magnetic or mechanical to obtain those particles which are on the required size. So it's screening here. If the particles have still larger size, they are turned into crushers to be crushed again so as they may become the required size. So the process of returning the oversized particles into the crushers, that process is called the screening. So there is a process called the screening there. But also these small particles now are being ground into the fine particles. Those particles which are not fine as required, they are just turned back into grounders to be ground again. So those that process of returning the oversized particles into the grounders to be ground again, that is called the classification. So these particles, the fine particles, are being classified. Classified. And what is done here is done through the classifiers. And the classifiers can be of three types. Can also be magnetic, can also be mechanical one. So it depends on the image by which it uses. So we speak about it. So speaking about that first steps about the grinding, that's what we do. So in every method that you're extracting, these steps are the same. So, for example, if I'm just starting to extract, okay, I'll talk about this later. So let me speak about the concentration now. Speaking about the concentration, what does it mean? Concentration. Speaking about the concentration. Let's go for the second step. I told you, just scream about the glycol rep. The second step, which is glycol concentration. Speaking about the concentration, we are just speaking about the method of removing the impurities from the metal, metallic ore. So removal of impurities from the metallic ore, the metallic ore. So the removal of impurities from the metallic ore is what we say the concentration. Now you concentrate the concentration of the ore. That's why you say the concentration stage, the core. So what happens here? It depends on the just come and listen well. Take it serious, man. Concentration depends on the type of the impurities and the type of the metal, the position of the metal in the reactivity series, and the type of the impurities. So, for example, speaking about the concentration, there are three methods that can be used to concentrate a metallic ore into a metal. So, how do you do this? We do it in three steps. Three methods. Common methods used. The first one is the gravity method. The second one is what we call the frothy flotation. flotation. And the third one is what we speak about the gravity method, the fourth flotation, and the magnetic method, method. So speaking about these three methods is what we say the concentration. What does it mean about the gravity method? What is done in the fourth flotation? What is done in the magnetic method? So let's start with the gravity method. Gravity method, this depends if the impurity and the metallic ore differ in density. So if the metal is more denser or the impurity is more denser, the one which is less denser will just float on the surface. So speaking about this, the gravity method is when they differ impurities and metallic ores differs in density. But speaking about the fourth flotation, how is it done? Let me show you. Here we just use those who lives in those areas, the mining areas, knows about this. So for example, this is the stroke now, and we have just corrected. We have some woods. So we have some woods which has been arranged in such that the fine powders coming from the first step, which is grinding, is washed with water, and then since metals are denser, we just stack here, while the impurities and water will just float downward. Water and impurities, but the metallic ore will just stack. On the surface. So what we do is just putting water on the fine powders of ores. That's what we do. In what we say the gravity method. So the impurities are just washed by water so as to remain, so as the metallic ore to remain inside those sites. So let's speak about the fourth flotation. What's about the fourth flotation? Fourth flotation is very important to understand this, because this is a special method of concentration. What we do in fourth flotation is we mix the fine powders with the water and with the pine oils. So what we do here is we take the fine powders. So speaking about the fourth flotation is we mix the pine oil. We mix the pine oils. We mix water. And then we allow the air to pass through a compressed air to pass through this mixture so as to form the agitation, the immersion. So when the immersion is just formed, the froth will just be obtained on the surface. So the froth flotation. The froth now is the mixture now which contains that metallic ore, the pure metallic ore, after removing the impurities. So when we mix actually the metallic ore, the impure metallic ore, we mix water, we mix pine oil, and then allow or force the compressed air inside. Then the mixture agitates itself and forms the immersion, forming the froth at the surface. So the froth is taken with a lot of concentration of the metallic ore, while the impurities falls down within the container, and then we take the froth to move to the third step, which is the calcination. So that's the method of froth flotation. But how about the magnetic method? How does magnetic method work? How does the magnetic method work? The third, which is magnetic method. Let's start about the magnetic method. Magnetic method actually depends on the property. If the difference between the impurity and the metallic ore is about the magnetic properties. So these are just used, for example, specifically exactly is when the iron in the extraction of iron. So speaking about the magnetic method is when the impurity and the metallic ore differs by magnetic properties. That's only where it's used. It's when, for example, in the extraction of iron. So what happens? What happens here is when that fine product coming from the grinding step is passed along the magnetic drums. So there are magnetic drums here, up and down, and then the fine powders are just allowed to flow through. So the metal, this containing iron, the magnetic metal will be pulled from the mixture, from the fine powders, fine powders, fine powder. So the metallic ore, pure metallic ore, will be pulled up to the magnetic drums, magnetic drums, drums. That's how we do for the metallic method of concentration. So speaking about the third step, actually, let's speak about the third step. I said, as normal, I said we have the grinding, so speaking about the grinding, we obtain the fine powder. Speaking about the concentration, I've said there are three stages that we have discussed about: the magnetic step, magnetic method. We discussed about the froth flotation, very important, froth flotation, and the third one is about the what to speak about the gravity method. Okay, so there are three things. Okay, how about the third step? The third step is actually talking about the calcination. What's about the calcination? Calcination. Speaking about the calcination, this is now the process by which we burn out the metallic ore, the one which has been concentrated, the pure metallic ore, not the pure metal, the pure metallic ore, not the pure metal, pure metallic ore is burnt either in this step, either in the presence of much oxygen, roasting in much, or we say excess oxygen, burning in the presence of excess oxygen. But calcination is in the limited amount of oxygen. So we burn in the limited amount of oxygen. That's what we say about the calcination. So which type of the metallic ore is being calcinated? It's the one which is not an oxide. So speaking about the one which is being roasted is the one which is an oxide. So speaking about this, let's say, for example, if I have aluminium, the bauxite now, which is O3 with the 2 watt of crystallization, this one, since it's an oxide, can't be roasted because the aim for roasting is turning the metallic ore into its respective oxide. So speaking about the aim for roasting is turning to oxide. But speaking about the calcination is just to remove, to dry out the metallic ore. For example, this one has a water of crystallization. So to remove this water of crystallization, you just heat it. So you heat it, but in the limited amount of oxygen. Dry to remove volatile substances. If there is, for example, sulfur, it just when you burn it in the presence of limited amount, it just goes out as the sulfur dioxide. So to remove volatile substances like silicon. Silicon can just be, when heated, can just be moved out as the gases. So those are about the limited amount of oxygen. Volatile substances, water of crystallization, like in aluminium, water of crystallization. That's the aim. That's the aim, bro. That's the aim of the third step, the calcination step, which is is just to remove those things. Okay. So let's speak about the reduction process. What's about the reduction process? Let's speak about the reduction process. Okay. So speaking about the reduction process, it depends. I've told you extraction always depends on the position of the metal in the reactivity series, meaning the nature of the metal. And the second thing that it depends on the type of impurity that is being found. For example, in concentration, as I spoke, the fourth flotation depends on the wetting properties of the metallic surface, the nature of the surface, of the metallic ore. So if the surface, for example, the impurities are hydrophilic, while the metallic ore are hydrophobic. That's why they tend to attract the pine ore and float out on the surface, while those impurities, since they're hydrophilic, they have the wetting properties to water, so they are just wetted and fall down to the container. That's what we speak about the concentration method. Okay, so speaking about the fourth thing, the first thing is about the reduction. Step is about the reduction process. What is done in the reduction process? Reduction is always now the turning of the oxide which has been formed here, or which has been dried here, into a impure metal. So now here we just obtain the oxide. Here we obtain the fine powder. Here on concentration we obtain the pure ore, meaning we purify the ore. And calcination, we obtain the oxide, which is now reduced so into a metal. And then this metal becomes purified here. That's how we do in extraction. So, okay, let's start. Let's do about the reduction process. Reduction process, there are 5 methods that can be used here. 5 methods. The first thing, we say you can just heat it. For example, iron, you just heat it in the furnace. So we say thermal reduction. So what's the reduction? Actually, reduction process is just the formation of the impure metal from the ore. So the conversion of the pure ore into impure metal, which will just be purified in the last step. So speaking about the thermal reduction, is when you heat into high temperature you heat into high temperature and turns into a metal. For example, things like mercury oxide, which are not very reactive, you just heat it then to form the mercury with some oxygen. Do you get that? Okay, so things like there are things like this specifically is for less reactive metals. Okay, let's speak about the second thing. The second thing is about the electrolysis. Electrolytic reduction. You can reduce a metallic ore just by using electrolysis. What happens? You just take that impure ore and put it into anode. Now it can dissociate. For example, here reduction. So we take the impure metal, which for example anode. You put it into anode. The impure should be pressed into the anode. So speak about for example, this is the metal now, the metallic ore. This is the solid now. So what is happening in the anode is just the oxidation. So oxidation is the losing of the electrons. So the metal tends to lose, for example, the 2 electrons. Let's say like that. Or if it's a certain number of electrons that it loses, even if it is 1. That's what happened. This will be the aqueous. Well, this is the solid. Okay, that's about the electrolytic reduction. Speaking about the other thing, but no, you have the cathodic reaction. You haven't discussed about the cathodic. So in every electrolysis, you describe about the electrolytic reduction and the cathodic, anodic, and cathodic reaction. So speaking about the cathodic is the reduction. So the reduction is the metal. We have the 2 plus the Ne. No. We have the Ne. We have the plus. Then E going to form the metal Mn, which is the salt now, guys. It's a salt. Yeah. Now we have the aqueous being reduced, meaning we acquire the electrons to form the metallic ore. That's what we speak about the electrolytic reduction. Depends. The third thing that we need to discuss here is about the third thing is it can be by precipitation. Reduction by precipitation. Reduction by precipitation. Precipitation. So what happens here in precipitation? You just choose a specific reagent that can make the precipitates of a metal from its respective ions or the fused form. So actually we precipitate. The formation of precipitates is what the reduction of precipitation. This is specifically is done in silver. Silver. Using the silver cyanide. Silver cyanide. So you can just obtain the silver by just precipitation method. So the precipitation method is just the reaction of salts, to form the insoluble or PPT, precipitates of metals. So you take a certain reagent, and then you mix with your ore. Then the metallic ore is obtained as the salt, while the remaining ones are those impurities as the liquid. So the formation of the metal as the PPT is what we say by precipitation method. The fourth thing, you can just reduce. For example, we have done about the thermal. You can use the reagent. You can use a specific reagent to reduce. Reduction by reducing reagent, reducing agent. You can use the reducing agent. This is one of the methods in reduction process. So you can just use the reducing agent. For example, reducing one of the reducing agents, carbon. Carbon you can just use, for example, let's say about in iron. Iron is tends to be as iron oxide. Iron 3, let's say iron 3 oxide. And 3 plus the carbon. So 2 here. Plus the carbon here can just go and form the carbon dioxide, but plus the iron, who is what? Who is the metal? Do you get that? This process is by using the reducing agent. So you heat it in the furnace. We'll discuss it later. Even in what we speak about the copper, we just use the reducing agent, either carbon or the carbon monoxide. All the transition metals, for example, iron. We can when extracting about the chromium. For example, when manganese. So, for example, for chromium and manganese, we can just use aluminium instead of carbon, like in copper. In copper, we just use carbon and carbon monoxide, and this one, carbon and carbon monoxide. But in chromium, the aluminium is well used. So it depends on the nature of those elements. So those are the 5 methods of reduction process. It depends now which type are you. Which metal and which type of impurities are you extracting from? Okay, so let's do about the last step, which is the purification. Oh, the self-reduction, man. I've forgotten about the self-reduction. Speaking about the self-reduction, the fifth method. I told you there are 5 methods for the reduction. So self-reduction. So speaking about the self-reduction, here is when the product of the same reaction acts as the catalyst for the same reaction. So we speak, for example, if A, let me give the really example. Speaking about the self-reduction, is the method of reduction in which a product or a byproduct acts as a catalyst for the reaction. So you take just a small amount of the part and burn it in oxygen. For example, if this is let's say it's the copper sulfide, copper sulfide. You just burn it in oxygen. Burning it in oxygen can form just a part of it, can form the copper 1 oxide and the sulfur dioxide. So this, as the gas is being removed, but this one as the solid is used now to reduce more copper sulfide. For example, if you have a large amount of copper sulfide, you just take a part of it, roast it, then you form the copper 1 oxide, and which is the one will be used to reduce the whole amount of copper 1 sulfate. So let's speak about, if you take this copper 1 oxide, then you burn it with copper 1 sulfate, what is going to be formed here is 60 copper liquids, and then you have the sulfur dioxide. This is what to speak about, and we can just balance this for copper and sulfur, so I can just balance here by 2. Yeah, so 2, 2, 2, 6. Yes. Speaking about this is the solid, well, this is the gas, it's being emitted. So we have the impure, we call the blister copper. This is happening at the self-reduction. So by summarizing what I've just spoken, is saying that the reduction process has the 5 methods. The first one, the self-reduction. We said about the reducing agent. We said about the precipitation method. We spoke about the thermal reduction. So those are just the methods of reduction in extraction of metals. Okay, guys. So let me go for the purification method. Purification method. The last step is the purification method. What is happening in the purification method? Purification method. Purification. This depends also. This is always done by electrolysis. So you just put the impure metal. Impure metal is placed at the anode. Why? To be oxidized. Then oxidized. When oxidized, turns to be the aqueous. So the solid is turned into aqueous. At the anode. But speaking about the pure is being pressed at the cathode. Why? So as to provide the electrons. Here is what is done, reduction process is done here. So for example, if it's the blister copper now, if this is the electrolyte, you know about the electrolytes, and then we have the electrode, we have the electrodes, and we have the electrodes. So this is the positive one, this is the anode, and this is the cathode. So what is being done here, for example, this is the copper. So the copper here, what happens, this the solid, because it's oxidized the solid into the copper ions, which is aqueous, plus the 2 electrons, according to its valence. So what happens here, this one turns into aqueous, the solid, the electrode turns to be the aqueous, so falls into the solution here as the copper ions. While the process proceeds, now this one is being reduced like that. So it changes its shape finally to be reduced. But speaking about this impure, these aqueous then are being reduced by receiving the electrons from the electrodes and then being deposited on this side of the cathode. So at the cathode, what happens is the receive of those ions in terms as the solid, solid ions, as they receive those electrons. Speaking about that, we say about the purification now. This is where, in this electrode, is where we obtain the pure electrode, where we obtain the pure copper, while the impure one, which is the blister copper, is being deteriorated after a time, so it disappears. Okay, so speaking about those steps, that's the part 1 of extraction of metal. Okay, so let's speak about those selected metals. Let me teach you how you can just use those steps to extract any type of metal. One of the problems here is when students it was 2022, I think 2022, there was one question of extraction for iron, and the syllabus only guides for the 3 metals. We have the tin, the copper, and aluminium. So students were wondering, why do they take us out of syllabus? Why they've just guided into 3? But actually, you have been told about the steps, so you need to know how to use those steps to extract any type of metal. These steps are the same, guys. It's easy to determine it. Let's speak about it. For example, so you're just going to start with the tin, selected metal. This is part B. Selected metals now. extraction of selected metals. Selected metals. So speaking about the tin, then I'll speak about the aluminium. So you need to know about, speak about this. The same steps, guys, are used there. I said grinding, concentration, glyco-carep. Hey, in order to any extraction process has these steps. If you forget, just remember, grinding condoms can reduce your purity when sexing, and then the condom bursts out, or you grind it, so you just reduce your purity because you get some transmission of STDs. So you can reduce the purity. You can just say grinding condoms can reduce your purity, guys. Purity. That's what we say about the Greco-Carib. But this is just the mnemonics. So when you grind your condom, can reduce your purity. That's what we speak about that. So speaking about the tin, what's about the tin? Speaking about the tin, you need to know about the grinding step. Grinding. So you just say, exactly. You just pick it as the paragraph, but following exact steps. So you say, for example, here, 14 now, I just say, no, you need to first know the natural existence. Tin tends to exist as, the natural currents tend to exist as the casterite, or we call it the stannic oxide. Stannic oxide. This is the natural existence, bro. Before doing anything, you need to know about the natural existence. So the natural existence is now the stannic oxide. So the first thing that you need to know is the grinding step. So you say the stannic oxide now is ground into the fine particles. Ground into fine particles. We call the fine powder. So this is the first step, the grind. Then let's speak about the concentration. Now the fine particles is being concentrated. You specify exactly. In the concentration, I told you there are 3 steps, and in the reduction process there are 5 steps. So you need to classify exactly when you're speaking about the metal. You need to be exact to the specific method depending on the type of the impurities and the type of the position of the metal in the reactivity series. So speaking about the stannic oxide now, 16. You can say the concentration, we have the gravity method, we have the flotation, and we have the magnetic property. This is not magnetic. Tin is not magnetic. Tin is not it's different with its impurities with the oxygen. It's not about the density because the oxygen is the gas and this is the metal. So it's not about the density, but it's about the flotation, the wetting properties. The tin tends to wet in. To be wetted by the oils, while its impurities tends to be wetted by water. So it's hydrophobic to water, while it's hydrophilic to oil. So speaking about the stannic oxide now, you just say stannic oxide is ground into fine particles or the fine powders, which are then added with the water and fine pine oils, and then agitated. So you just speak like explaining the first rotation, then agitated by a compressed air, so as to form emulsion. So what is emulsion? The mixture of salt and the liquids, while the salts form at the upper sides. So the froth is obtained because it's hydrophobic to water. So it's obtained just at the above, where froth is obtained at the top. At the top, because what's the reason? Reason to be at the top is because it's hydrophobic to water, so it's wetted by the oils. So that's the second step. The first step, So we obtain now the froth. The third step, which is now the calcination. So since the stannic oxide is an oxide, the only process here is done under limited oxygen, which is the calcination, not the roasting. Calcination and roasting process. But this, since it's an oxide, it's just being calcinated. So the froth obtained, the third step, the third step now, froth obtained is being calcinated, calcinated in limited amount, limited oxygen. So what happens here, bro? What happens here in calcination? We turn now the stannic oxide into a concrete dry substance. So what is happening here is drying it, drying, and removal of volatile substances, removal of water crystallization. So that's what we do, just heating it, just to make it dry before reduction process. And the reduction process that is used in tin is just by using the reducing agent. So the reactions here, the fourth step is reduction by using reducing agent. And here you need to describe about the reaction. Hey, you can describe this extraction without a reaction. So you need to show here a reduction process of the using agent. For example, here we have the stannic oxide. Now we plus the carbon. If you use the carbon, what happens here? And it is done in the furnace. Furnace. You heat it to high temperature, but using the reducing agent, which is being turned into carbon dioxide and tin. Tin as the liquid now. So the carbon dioxide, yes, this is the solid, this is now the gas. Now the gas is being emitted and you tap it as the tin. So that is the first step, which is reduction by using the agent. The fifth is the purification process. For example, if somebody can use the carbon monoxide instead of carbon here, the carbon monoxide instead of the carbon here for tin, now you can just say, if I use, for example, if I use the carbon monoxide, for example, the stannic oxide now, I use the carbon monoxide to form the carbon dioxide and the tin. What happens here, bro? This goes direct to form the carbon dioxide. But speaking, no. Yes, it's okay. Okay. So speaking about the stannic oxide, we have the carbon dioxide just goes and form the carbon dioxide. Okay. So speaking about this is carbon monoxide. This is stannic oxide. Where we have yes. You can now balance this. Okay. So speaking about this, we can say the purification method. What is done in the purification method? The last step, the fifth step, purification. Purification is done by using electrolytic cell, electrolysis. So what happens that impure is being pressed, I told you, at the anode. So we put in the impure tin. At the anode. How do you know the anode? You just press it. Anode. You just press it as the positive here. As the negative, this will be the cathode. So as the cathode here, this is the cathode, which is now the pure. So what happens here is the reduction. The tin from the electrolytes are now pulled by electrons. So tin positive ones receive the electrons and become the solidifies, but at the electrode side. So the deposition occur here as the solid. But speaking about really, this is about the reduction, the oxidation process. What happens to the oxidation process is SN. Then the solid is just turned into ions, which now dissolves and to be reduced at this side. So we have the tin, but we have the positive, the aqua plus the two electrons. That's what's happening. That's what's happening, bro. That's what's happening. So speaking about the copper, let's speak about the copper. The second thing is about the copper. Extraction of copper. Let's speak about the extraction of copper. Extraction of copper. Extraction of copper. Let's speak about the extraction of copper. Extraction of copper. Let's speak about the extraction of copper. Copper extraction. So speaking about the copper extraction, the second metal is about the copper. Copper extraction. The same thing, bro, that we used. Correct. You need to grind, you need to concentrate. You need to calcinate or roast, depending on the nature. If it's an oxide, you calcinate. If it's not an oxide, you roast it. Reduction, and then you purify over about the extraction. So let's speak about them. Before I speak about the extraction, we need to know about the uses and the chemical properties. In every metal, and these selected metals, you need to know about the uses. For example, one of the uses, let's speak about the uses of tin before I leave. Before I leave, you need to know about the uses of tin. What is tin being used? For example, we have the tin fluoride. This is used as the toothpaste. Used in manufacturing of toothpaste. Toothpaste. This is most used in manufacture of toothpaste. The second thing is also used to manufacture the metallic alloys. Metallic alloys like bronze, the solder, composes the tin. So metallic alloys. Metallic alloys is very important. Alloys. They are very important because they improve the physical properties of the metal. Metal, you can find it high conductive because it's a metallic alloy. You combine it's a solid mixture. Metallic alloy is a solid mixture of the metals, so it improves the properties of the metals because the effect will be the effect of the two metals actually. So speaking of the metallic alloy, for example, we can have the solder, the one which is used to join the metals by just using it by using electricity. That's why solder is 50% reed and 50% tin. So that's the solder. How about for example, bronze? Bronze also is a copper. Copper 74%, but tin 24%, 76% about copper, and then 24% about tin. That's a metallic alloy, bro. That's a metallic alloy. The uses of the tin. Tin also can be used in tin planting, bro, to protect it from from what we say, chief. What we say rusting. Yes. So rusting destructs the metals, but when using a tin is less reactive to form it can't allow the metal to form rusting. So speaking about the third is tin planting. So you plant on the metal tin. Why? To protect it from protecting from rusting. Something we call it rusting, to protect the metal. Tin planting, and it's very important than galvanization. The other method is to protect it from the rusting is galvanization. Galvanization. But the reason galvanization is less important like tin planting is because this one in the process, this is the use of zinc, coating zinc. You coat the zinc on the metal surface. So this one, the processes of galvanizing is poisonous. It's poisonous, so it can't be used to coat out the spoons, those food containers. So we just use the tin instead of zinc, because this one, process of manufacturing, the process of coating is poisonous. It involves the poisonous substances, poisonous substances. That's what we speak about the uses of tin. There are also reactions, chemical reactions of tin. Before you move to copper, you need to know the uses, the chemical properties actually and the methods, how to describe the methods of extraction of that metal. For this selected metal, even in aluminium, we discuss about the how to extract aluminium, the uses, and their physical and chemical properties. For example, talk about the physical properties of tin. Physical properties of tin. Physical properties of tin. Tin always exists as white or gray. Why? At 13.2. So below that temperature, 13.2 degrees centigrade, what is find? It's gray in color, but above that, it acts as a white. These are the two allotropy. Two allotropy of tin. Allotropy. So allotropy. So it have the two physical appearance, two different physical appearance of the metal. Two appearance. So speaking about the chemical properties, let's discuss about the and to remember this, the gray one is the dark. This means the temperature has been increased. While this one white, it shines, dude. That's why it's white. That's why you can just remember the allotropy. It can't disturb your mind to claim it. When you have that concept, that's white has high temperature. Let's speak about the chemical properties. The chemical properties now. Chemical properties. Properties of tin. Tin. This here there are four. Let's say 4 or 3 chemical properties. Very important to understand that tin about oxygen. How does it react with the acids? How does it react with the bases? That's how you need to know. That's all what you need to know. So, for example, tin can't react. No reaction. No reaction with the oxygen. No reaction with the oxygen at the normal conditions. At just normal conditions, no reaction with the tin. But tin can react with the oxygen when heated to high temperature. It can just react and form the stannic oxide. The stannic oxide. That's what we speak about the reaction with the oxygen. But also tin, so it's non-reactive to oxygen or to air. But speaking about the second thing is about the acids. Speaking about the acids, bro, number 2, this is number 1. Acids, reaction with acids. How does it react? Acid, the tin, it depends on the type of acids. There are those which are non-oxidizing and there are those which are oxidizing. So speaking about the non-oxidizing, like sulfur, HCl. So acids here, it depends. Depends if it's a non-oxidizing, like HCl and the sulfuric acid, and we have the oxidizing, like nitric acid. So speaking about this, the oxidizing, for example, when the acids react with the oxidizing, after they are turned into, they tend to release, and it depends exactly. It depends if they are dilute or concentrated. If they are concentrated, for example, if they are dilute, let me speak about the dilute. Dilute acid, acids. Speaking about the dilute acids, then I'll speak about the concentrated. If we have the dilute acids, we just form the hydrogen gases. Releases the hydrogen gases and forming the salts as normal. It's a metal, bro. It's a metal. It's like a magnesium put into HCl. So what happens here actually for the dilute? What happens here is, for example, I have the tin, then plus the HCl. It actually goes to form the tin, which is tin chloride as the salt, but we have the hydrogen gas. So this is the signification that it has just reacted with the dilute HCl. Tin also can react with the dilute sulfuric acid to form the tin sulfate. But what sulfate with? Here also the other thing is about the chlorine. It can react with the chlorine. That's the chemical properties, bro. So speaking about the oxygen, we have discussed it. speaking about the acids, we have the dilute and the concentrated. So for the dilute, it depends if they are just dilute and non-oxidizing, like these ones, it just forms the salt, but it releases the hydrogen gas. But speaking about the oxidizing acids, and here is about the nitric. Nitric turns it into we say the just the complex mixture. It forms the nitrates, it forms the ammonium nitrates, and it forms the just some other products depending on the ratio of the amount that is being used. It's from the complex products, complex product of different products. Okay. Let's speak about the reaction in acids. If we have the concentrated acids. Ambayo nimekwambia the concentrated acids, it can be oxidizing, mean this is, for example, nitric, and non-oxidizing. This can be what we say the sulfuric acid. Let's say sulfuric acid, for example, the sulfuric acid. When they're acting, for example, with the conch sulfuric acid, what happens here? It just forms the tin 2 sulfate. Tin 2 sulfate. But why this one just forms this one actually forms the complex. This one we speak about the oxidizing complex products, different products, forms different products. Here we just form the tin sulfates, and here we just tin 4. While we speak about the concentrated, we speak about the oxidizing acid, which is nitric acid. When the nitric acid reacts with tin now, which is conch, for the dilute it forms just the complex mixture. But this one, it oxidizes it into tin oxide, and it forms its respective. It can just form water, and it can just form the gas which is being used, the dioxide gas, and also the same thing. It forms, but this, since it is not that oxidizing much, it just forms the sulfate, the salt, and then that gas should be formed, the dioxide gas, depending on the type of the acid, dioxide gas and water. So those are just the products. But actually, speaking about the reaction of tin with the acid, it depends. Either the acid is oxidizing or it's non-oxidizing. If it's oxidizing, it will just oxidize it much. For example, here it just oxidizes it into stannic oxide, while here just oxidizes it into salt, which is non-reducing. So this is for concentrated, and if it's dilute also, it have its own reactions, because the concentrated and dilute, concentrated are more reactive. Now let's speak about the reaction with the bases. How is tin reacting with the bases? Even with the chlorine, tin with the chlorine, it turns into tin 4 oxide. Tin 4 chloride. Let's say tin. We have the tin now. Tin plus the chlorine gas. So what happens is stannic tin 4 chloride. So that is tin. It turns into tin 4. So, but talking about the bases, how does it react with the base? So water, you plus with the centenary base, this potassium hydroxide, sodium hydroxide, but you plus with tin. What happens here is tin now turned into a complex. Tin, let me take it as water. Here, let's form the complex here. Look my boy here. This is what we call the hexa aqua stenate 4. This is a complex. So we'll just discuss about the naming of this complex in the next chapter about the transition. Hexa aqua. Aqua. Hexa is this 6. We have the 6 molecules of water. Stannate. So this is the complex. We will just discuss it in area. So those are the chemical properties of tin. Dang. So let's go to discuss about the copper, extraction of copper, and then finally extraction of aluminium. Extraction of copper, and finally the extraction of aluminium. Finally, the extraction of aluminium. Extraction of aluminium. Okay. So guys, here we go. Here we go. When speaking about the extraction of copper, speaking about the extraction of copper, we speak exactly about glycol carep. What is so when you start to speak, you just say the chief ore. Which is the chief ore? Is the we say the copper pyrites. Copper pyrites. Speaking about the copper pyrites is copper, iron, but Sc2. So what is being done is the copper pyrites is the pyrites are ground into fine powders. To fine powders. That's the first step, chief. First step before going anywhere. That's the first step, chief. The second thing is about the concentration. What is done in the concentration called. So you just say these powders are mixed with powders, fine powders. In the concentration is the froth flotation. So what happens in the froth flotation? The fine powders of pyrites are mixed with the pine oils. Then mixed with water, and then agitated, compressed air, agitated by compressed air. By what? A compressed air. To turn what? Into form emulsion. So what? We obtain the froth from the upper surface. So the froth is now taken into the calcination step. What is the calcination step, bro? Calcination. Okay, let's speak about the calcination. Number 3, calcination. So what is being done in the calcination? Because this is not it is not the oxide. It's copper pyrites, copper, iron, and sulfur. So what is being done? And the criteria for the froth flotation, you must have the sulfur, like that, and sulfur is impurity. So, so we say the calcination process. We roast it. We calcinate and we roast it because it's not an oxide. So it should be turned into oxide. So it's burned in excess, not limited oxygen, burnt to form. What happens now? Look here, you need to put these reactions. So this copper pyrite is being turned when heated in oxygen, plenty oxygen. What happens is copper is turned into copper 1 sulfide, and then this iron turns to be iron oxide, the solid, and then this sulfur turns to be the sulfur dioxide, and it's moved out as the gas. So this moves out as the gas, while remains the mixture of iron 2 oxide and the copper 1 sulfide. So what happens? How do we separate this? We just add the silica, the second step. So the first step is just heating it in calcination and roasting, and then you add the silica. The second step is the addition of silica. Add silica, silicon dioxide. So what happens here when you add silicon dioxide? It takes these ones as the molten slag, iron oxide. It turns into iron silicate. These are the molten slag. They are just moved as the molten slag. We say molten slugs as the liquids. So the solid heated to form the liquid. So this also is being removed. While this one remains at the solid, the copper 1 sulfide. This remains at the solid. So what happens here? what happens here now? This one is taken into the reduction process, which is the self-reduction. So the self-reduction now is this one. A small part of it is being roasted, is being burned in the certain limited amount of oxygen. Then it turns into oxygen, into copper 1 oxide. The copper 1 oxide is then used to reduce the whole amount of copper 1 sulfide. So a part of copper 1 sulfide is burned so as to produce a certain product, which will now be used as the catalyst to oxidize the other remaining parts. So we're saying this one is being self-reduced. So how is the self-reduction done? It's just by burning it into oxygen, and then we form the copper 1 oxide. Copper 1 oxide and the sulfur dioxide. So this one is removed as the gas, while this one, copper 1 oxide, which has been formed now, is used, is again burned with the same reactant, copper sulfide is mixed to form now the copper, which is 6 liquids, more atoms, and then we form the dioxides. So they are just removed as the dioxides, and here you can just balance it by 2 to get the 6. That's how we do. This is the self-reduction. This is the self-reduction. This is the self-reduction process. This one. Then the obtained here is the blister copper. It's not the pure. It's the blister copper. This means it's impure because there are some percentage impure. There are some percentage copper, impure copper. There are some percentage of impurities still in the container. So we say in the crystal, in that liquid copper. So we say now. Let's speak about the purification method. How do we do the purification method? For purification method of copper, as I've told you, purification is always done by electrolysis. Purification is always done by the electrolysis. So speaking about that, we take that blister copper, which is now the impure, and put it at the anode side, the positive. So this is the positive, this is the negative, and then we put here the blister. This is the blister copper. This is the blister copper. And then in the electrolytic cell, we have the electrolyte as normal electrolyte. This is the electrolyte. This is the electrolyte. This is the electrolyte. This is the electrolyte. So speaking about the electrolytes now, we have what we speak of. This is the cathode. So this is the anode now. The blister copper is at the anode. So what happens to the blister copper is anodic reaction. Anodic reaction is, we say, the copper now, which is the solid, is being oxidized into the copper ions, which is aqueous now, and we have the 2 electrons. So we turn out the solid, and it's broken down into the ions. So the solid, the copper solid, is turned into the copper ions. These copper ions now here at the cathode. This is the cathode. This is the reduction process happening here. Reduction process. So what happens? These aqueous which have come into the solution are pulled in from the solution back to the electrolyte, which is the cathode. So what happens is the copper, the ions from the solution now, they against the 2 electrons, that these ones comes from the electric cell here, and then they reduce it into the copper solid. That's what the deposition tends to occur at the side of the cathode. That's what we say the purification. So the whole crystal here at the cathode is the pure. It's the pure. It's the pure copper. While the impure is being broken down into certain, so as to obtain those ions. Okay, that's about the extraction for copper. Let's discuss about the extraction for aluminium. 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 Oh, the uses and the chemical properties for copper. Copper is actually used here. Copper, uses of copper. Uses of copper. Copper is used in electrical kettles, electrical wires, wires to manufacture the electrical wires, and since they have much conductivity, they can just be used also to make those cooking utensils, cooking utensils at home. They can just be used as the let's say the metallic wires, the electrical kettles, electrical kettles. Yes, since also they are hard, copper can be used to make the metallic ores or the orbital metals. So it can just be used, for example, to make the metallic alloys like bronze, bronze. Yes, things like that. Because we're talking about the bronze actually is 76 copper and 26 tin, 6%. Yes, 24% is about the tin. That's what we speak about the usage of copper. Let's discuss about the aluminium, extraction for aluminium. God damn, I'm so tired, guys. Let's speak about the aluminium, extraction for aluminium. What about the aluminium, bro? So speaking about the aluminium, exactly the same steps, my dears. So we just use the glycol carib. So what happens in the glycol carib? You just grind. So you just say, what's the chief ore? It's bauxite. There are many ores, but when we speak about the chief ore, when I speak about the chief ore, this means it's economical. What does it mean to say economical? Means within a small amount, I can obtain large amount of metal. When I say something is not economical, meaning I just use large ore and obtaining very small amount of metal. That's what I speak about. So speaking about the bauxite is what I'm saying. Bauxite is the chief ore, meaning I can just obtain a large amount of metal from the metallic ore. So speaking about the bauxite now, let's discuss about now the bauxite. So the first thing is that you can do is grinding. So the bauxite actually, bauxite is being ground. What's the reason for grinding? Is to obtain the fine powders. So what happens to the fine powders? Fine powders, so as to increase the reactivity. The reactivity means this bauxite can be concentrated, can just be moved into concentration. Then the concentration, there are 3 steps that can be used. Can it be gravity method? Can it be the magnetic method? Or can it be the froth flotation? So the aluminium, we just use the froth flotation. But what happens here? There is one stage which is being added in the steps here for aluminium. Aluminium here, we grind, then we concentrate. On the concentration, we need to purify. Instead of concentrating it, we purify. For aluminium, the bauxite ore, we grind it into fine powders so as to increase the reactions. But actually, the second step now, which is now either the froth or the gravity method or the magnetic method, we don't use this. We omit this by concentrating it by the 3 methods that can be used for aluminium, depending on what you choose. So aluminium can either be concentrated, we say the purification of the ore. So here, instead of grinding, so for aluminium, it's grinding, but here is the purification of the ore. Instead of concentration. So we don't use gravity or whatever, no. The second thing, after purification, we can now calcinate it. After calcination, then we can now reduce it and purify it. So there are those 5 steps to be used here. Let's start with it. Let's start with it. Let's start with it. So speaking about the purification method now, after obtaining the fine particles are now taken to the purification. Purification of bauxite can be done into the 3 consecutive steps. The first step actually is about the first step, we can say the Bayer's method. If you don't use the Bayer's method, you can use the Hall method. If you don't use the Hall method, you can just use the third method, which is the Sapet method. So what happens here? Let's speak about the Bayer's method. Bayer's method is when you take now the Bayer's method. You take now the bauxite, aluminium with the 2 water of crystallization, then at a temperature of 200 centigrade or up to 250 centigrade, ranging there, and then 35 atm at a certain high pressure. This one can be combined with the sodium hydroxide. That's the first step in bio. So you just add sodium hydroxide, the base, on the bauxite. The base plus the bauxite. This one, when added at a high temperature and a high pressure, they turn into this one, the aluminate, sodium aluminate, and water. So what happens here is actually to balance this is 2, you can balance 2. Yes. You see? So balance for oxygen, for hydrogen, yes. So this aluminate, when added with water, it forms the complex, which is sodium. When you add 2 molecules of water, sodium aluminate. This is the complex of sodium aluminate when added with the water. So this one, sodium aluminate, the second step which is done after adding water, this is the same thing as this. So for other books, it's just writing this to this, to this, and then text this instead of adding water. So it's just the same thing. This is the aluminate. So the aluminate now, for the second step, this sodium aluminate is added with the carbon dioxide, but at a temperature of 55 degrees centigrade, so as to form the aluminium hydroxide. So what happens here is this mixture of water here added with the 2 water to form this one. So this one added with the carbon dioxide, the aluminate added with the carbon dioxide, it formed the aluminium hydroxide. Very important. This is the major product, and the sodium carbonate, this is we can have the carbon dioxide now. We can have the carbon dioxide. This is water, sodium carbonate. I can just form the sodium carbonate here. You see, because I have the sodium here, so I can just add here 2 to balance it. 2. Then it's my sodium is 2. The carbon, how many? 1. Then we have the oxygen, how many? Hydrogen, we have the 2, 8. Hydrogen, we have the, so I need to put here 2 also to have the 6. The hydrogen is 6. This is hydrogen. Then I need to plus water here. To plus water, this means I'll just have the hydrogen. This is 2, 8. Then here is 2. Then I have the 2, 8. For oxygen now, I'll just have the 6. Then I have the 6. This is 2. having this 6 and 9, 10. So I just have 2, 2 and 8, then I have the 10. So it's balanced. For inorganic reactions, you need to balance them. So what happens here during the bias method is just the 2 steps. The first thing you add with the sodium hydroxide to form the aluminate, and then the aluminate is being added with the carbon dioxide. You bubble it, the carbon dioxide inside it, so as to form what is aluminium hydroxide. Aluminium hydroxide. Okay. So obtaining this, you can just heating to form the aluminium oxide plus water. That's what you heat after heating. So this is aluminium oxide. This is the pure bauxite. After heating this, we obtain now the pure bauxite. So you have purified the ore. So this one is the one will enter into the calcination step. So if you don't use that method, you can use the whole method also to get this. How do you use the whole method? Yeah? The whole method is just combine. Getting me clear? It's just burning the sodium carbonate directly. So we have the aluminium oxide, the bauxite now, with the 2 water of crystallization. I just burn it directly with the sodium carbonate, burning it directly, heating. So I just form the aluminate, sodium aluminate with the water, water with the carbon dioxide. Do you get that? So this one proceeds at this stage, this one. So it's just added with the carbon dioxide and then forming the aluminium hydroxide, which is now heated to here. Do you get that? Yeah. So speaking about the third step, which is now the SAPEX method, is now burning it with the nitrogen and the carbon dioxide. If you don't use this or you don't use that, you just take the aluminium oxide and then burn it with the nitrogen gas with the carbon. So burning it with the nitrogen and the carbon, it turns into first thing aluminium. This is the major product, aluminium nitrite. Aluminium nitrite, this one. So balancing it by 2 for this nitrogen, and this is carbon. So you just go and form the carbon. This we can form here the carbon dioxide, and we can just form the nitrogen. Nitrogen. We have, yes, it's balanced. It's good. It's balanced. So this is 2 aluminium 2. So the oxygen is 3. So I can just put here 3, and then I put here this is 3, and this is 6. So this here is okay. So here is 3/2. So as to balance it, the oxygen and then carbon, I can just put up 3. 3/2 also. 3/2. So as to balance. Or you can just multiply over 2 so as to clear those 2. So that's about the SAPEX method. It's now the burning of the bauxite with the carbon and nitrogen so as to form the aim is to form. So in the SAPEX method, you just form the nitrite. This nitrite, the second steps in the SAPEX, so as to form the aim is to obtain the pure bauxite. So you just add water, hydrolyzing it. On hydrolyzing it, you result into aluminium hydroxide. You get that? Let me just do it there. SAPEX method. Let me do the SAPEX method here upward. Let me repeat the SAPEX method here. You just in the SAPEX method now, you just take the bauxite, aluminium, you burn it with the carbon with the nitrogen gas, goes to form the aluminium nitrate. That's the major product, bro. That's the major product with the carbon dioxide. So what happens is carbon, this is 3/2, so as to balance this, and this is 2, this is 3/2 also, while this is nitrogen, so it's as balanced. Then the second steps for the SAPEX is this aluminium nitrate, this is aluminium nitrite, then added with water, hydrolyzed, then to form the aluminium hydroxide, but with the what we say about the ammonia, the gas, the gas. That's what we speak about, bro. That's what we speak. So speaking about this can be turned just by heating into aluminium oxide. That's what we speak about the Sapex method. That's about the purification of the bauxite. That's instead, hey, we grind into fine powders, then we concentrate, glycol concentrate. Instead of concentrating, we just purify the bauxite. That's the step you need to know. This is a substitute in aluminium. So after purifying now, we have the pure aluminium oxide. The pure aluminium oxide now is being calcinated, yeah, to remove the water of crystallization and those which is substances which are volatile substances and different substances just by heating it. So the step, glycol concentration now, concentration step, glycocarepu. So this is grinding, then concentration, then we did the calcination now. We are doing the calcination. So speaking about the calcination, what is happening here is aluminium oxide is just being heat to remove water, volatile substances, and to make it dry. So drying it, yeah? That's what's happening. So let's talk about the reduction process. Reduction process. Let's speak about the reduction process. So really about the reduction process. So really speaking about the reduction process is about the reduction. I say the reduction can be thermal. Reduction can be thermal, I said. Can you be using agent? Can you be using what we say agent? Thermal? Can it be by electrolysis? Can it be by self? And can it be by precipitation? So speaking about the aluminium, we're just going to speak about the electrolytic reduction. So speaking about the electrolytic reduction, here is done in a specific cell, electrolytic reduction of aluminium. So what happens here? Aluminium is in the cell, which is in this form now. Let me draw the electrolytic cell for the reduction of aluminium. Electrolytic cell for the reduction of aluminium. Electrolytic cell for the reduction of aluminium. So aluminium can just be reduced by using this cell. This cell, bro. This cell. So we have this is the anode. Positive. While we have the cathode right here. Cathode right here. So this is so what happens? These are electrons, carbons. So what happens here? We have the rods, carbon rods, which connects with the positivity, which is now the anode. You get that? So speaking about this being the cathode is connected to the negative. So here is the electrolyte inside. Electrolyte inside. So what happens here is, if we talk about the aluminium, that aluminium trioxide is fused to be a liquid and then mixed with here inside fluorspar. What is the fluorspar? It's about the calcium fluoride. And the other thing is about the cryolite. Cryolite. Cryolite is about the sodium 3, aluminium but fluoride 6. That's about the cryolite. So speaking about the cryolite, what happens? What are the two functions? You need to know about the two functions of these in the electrolyte. So here in the electrolyte, it contains the cryolite, fluorspar, and the fused. This is the fused, meaning the solid now has been turned into fused bauxite. The purified bauxite is turned to be a liquid and then pressed inside as the electrolyte. So speaking about this, the two basic function of these things is to, because this is not much conductive, as it's not the much conductive the aluminium oxide. So these ones, cryolite and fluorspar, tends to rise its conductivity. So the function here is to increase conductivity of aluminium, and the second thing here is actually due to increase the conductivity and to reduce the melting point, because it's have high melting point, so reduce the melting point, MP, the melting point of the aluminium. So this mixture of cryolite and fluorspar have the two functions: to reduce the melting point and to increase the conductivity. Okay, so what happens here, we need to write. When you speak about the electrolysis and you don't write about the cathodic and anodic reaction, you are wrong. So totally you need to write about the cathodic and anodic reaction. So what happens here in the electrolysis now of aluminium here is about the and you need to discover about the electrolyte as I've described and the structure actually. So these are the carbon rods. This is the carbon lining, which is the cathode now, and this is the carbon lining, which is the anode. So what is anode? Anode meaning oxidation. So what happens is the aluminium, which is now anode meaning the solid, is turned into aluminium ions. These aluminium ions here, aluminium ions should be deposited here, should be deposited here at the cathode. So the cathodic reaction is the reduction. So what happens here is the aluminium coming from the solution, is being taken, aluminium. So from the solution, which is 3 positive, is being added with the 3 electrons to go and form the aluminium solid here. So aluminium is being deposited. This is the tapped aluminium, liquid aluminium here. So it's just tapped downward here. The outlet for this is the outlet for aluminium. So this is the aluminium, liquid aluminium. So what happens here? Anode as the solid now, as the liquid is being tapped here. While here we have the oxygen, which is now propelled at the anode. So we form the oxygens. So we have the oxygen, which is 2. Now in anode it tends to lose the electrons, so becomes positive, and we have the 2. So this as the gas turns to be aqueous. So what happens to balance this is 2 balances. The atoms balances to 10. So in order to balance the electrons, you can just multiply by 66. All these 4, so as to combine well. So speaking about the electrolytic reduction, here is the oxygen, oxygen formation. At what? At the anode. But here is the deposition of aluminium. From what? From the aluminium oxide. So the summary of this electrolysis of aluminium is the deposition of aluminium and the involvement of oxygen. That's why after time these rods should be repressed, because they tend to reduce in size after time, because oxygen tends to combine with carbon to form the carbon dioxide. So that's why to speak about the electrolytic reduction. Let's speak about the uses and chemical properties. No. We are in just the fourth step. The fourth step. So we discussed about grinding. We said about concentration. We said about the calcination. We said about reduction and purification. So we ground, we concentrated. Instead of concentration, we purified the ore. Not purification of the metal, but purification of the ore. Not the purification of the metal, but purification of the ore. And then calcination. So in calcination, we burnt it. Just in the limited amount. We calcinate instead of roasting, not roasting, calcinating. Then limited oxygen. Then we reduce it. How do we reduce the aluminium? We reduce it by electrolytic. So you need to know about to draw that cell. But there is purification. Purification is done in a special cell called Hoops cell. Hoops cell. You need to know how to draw it and how the purification is being done in the Hoops cell. Hoops cell for purification. So let's draw the Hoops cell for purification of aluminium. Hoops cell for the purification of aluminium. Okay, speaking on the Hoops cell for the purification now. Hoops cell. Purification by using the Hoops cell. Hoops cell is in this form. Yeah. First thing you need to know about the Hoops cell for purification have the 3 layers. 3 layers. So as you may not claim about how to draw it. 3 layers. The first thing is about the pure aluminium, which is pressed downward. So we have the basement here. We have the carbon lining here. Carbon lining as the cathode. This is just the carbon lining. Why carbon lining? It's a metal to hold the aluminium. So what happens is aluminium over here. Aluminium. This is impure. Aluminium. It's pressed here. So the first layer is impure aluminium at the basement. Below, upper chin, this one, this is aluminium. So this is impure, and it occurs as a metallic alloy of copper, aluminium itself, the impure aluminium from the reduction process, from the Hoops cell, and then with the silicon. So it occurs the metallic alloy here. So it's a impure aluminium. Then we have the second layer. Which contains second layer, bro. So we have this second layer. This one contains actually now those reagents to reduce their melting point and to increase the conductivity. So here we have those reagents like barium fluoride and cryolite. What's cryolite? The sodium 3 aluminium. Cryolite is, what's the reason for this? 2 reasons I told you. The first reason, number 1, reducing the melting point. The second thing is just by increasing the conductivity. That's all about my idea. So talk about this, we can just say this layer, the upward layer is about the pure aluminium. So acts as the cathode. Cathode, we say the pure aluminium. So we have the second layer. We have said the second layer is containing the electrolytes. Electrolytes. So the second layer is electrolyte, which is cryolite and the barium fluoride, the fluorspar. Do you get that? Then the third layer, which is now the pure. Third is the pure. So what happens? This acts as the anode. No, the cathode. What's the cathode for? Look here, the mechanism, how it operates now, how it operates. Before, this cathode is just connected to the negative side, negative terminal. Because this is the cathode, the pure. So what happens is a metal, the aluminium from here, from this electrolyte, is being pulled, being oxidized, because this is done electrolytically. So this, we have the cathode. This is carbon rods, to induce current here to the pure metal, pure metal. So what happens here? The mechanism. What happens in the hoops itself? What happens after knowing the structure that it have the three layers? What happens? What happens here is aluminium ions from the cryolite and this mixture, from the mixture, aluminium ions, then added with free electrons, then it forms the solid. So they freezes here. They freezes downward here, the pure cathode, attracted at the pure, the upper layer, the pure aluminium. While this one, this layer is being broken into the ions. So we say the aluminium, which is impure, broke down as a salt, break down into 3 electrons, but 2 aluminium, which is aqueous. This is the impure aluminium. This is the ions. Now, ions are attracted from the solution to here, to the pure, and then, since they have just left the deficiency of the aluminium ions, then the impure breaks down into ions, which are then coming to replace the one which has left from the concentration. So what happens is the same amount that of ions of aluminium that has been attracted to the pure cathode is then being substituted by the ions coming from the impure zone. So there are three layers, and the 2 actions. The first thing is to remove the ions from the electrolyte to the pure, and then the second thing is the replacement from the impure to that point. So guys, today I had the inorganic chemistry, and it was about extraction, copper and aluminium. So the last part will just be about the transition methods. We have discussed about the compounds of metal firstly, we discussed about the periodic classification, and so this is the third subtopic, which is about the extraction, and then we'll just go on for the last subtopic, which is about the transition methods. God dang, it's Kusekwa boy. I'm sending out.